So, should I get started? Okay. All right. So this is the conclusion. We're coming to the conclusion of the first week. We're finally ready to state the kind of main theorem of this week, which is this Hormander theorem in the sort of fullest form that we know. So the first thing I should discuss is what complete manifold means to us. Well, there's a lot of characterizations of completeness. And you can sort of see it in a number of equivalent ways. But the one I'm going to use is the following. So there exists an exhaustion. So say a C1. I just take a smooth exhaustion. C infinity exhaustion. Say H, not H is bad. Psi from X into R, such that, okay, so maybe I should have said, so our manifold is X with some Hermitian metric G, which will eventually be Kahler, but for completeness, I'll just discuss for general Riemannian metrics. Completeness means, the definition is that it's with this Riemannian metric, you can measure the distance between points as the infimum of the lengths of all paths connecting those points. And you can compute the length of a path with a metric. And completeness means that with this distance, you have a complete metric space. But there's a bunch of equivalent characterizations. And so the one I'm going to use here is that there exists an exhaustion whose derivative if you measure its norm with respect to metric G, that's less than or equal to a constant, which you can rescale the function, make it less than or equal to 1. So at all points of the manifold, say the sup over X is less than or equal to 1. That's one of the equivalent characterizations. I don't want to spend too much time on why this is the case, but if you're interested in figuring it out, so completeness means is equivalent to saying that if you try to find a geodesic, a distance minimizing path, then you can find one that goes on forever. So they don't exit the universe in finite time. And by using geodesics, you can make an exhaustion function like this by using the completeness. And then if you just move along at unit speed, you get this bound from such a function. The problem with that function is it's not quite smooth, so you will have to smooth it a little bit. But anyway, so that's the rough idea of why it is. But this is what we're going to use completeness for. And the point, which I'm not going to overemphasize, point here is to construct cutoff functions whose derivatives are uniformly bounded with respect to the metric G. So if you have such an exhaustion, you can compose it with a standard cutoff function to make cutoff functions with very, very small, with reasonably small derivatives. So, okay. All right. That's the first thing. The next thing is about approximation of twisted forms. So let me introduce some notation. we have sort of two d-bar operators. One of them I'm going to call T. So this is the d-bar, maybe I should say the maximal extension of d-bar from L2 NQ of GH to L2 N, sorry, this one is Q minus 1 to Q. Not much better. And then S will be the other one. Q to Q plus 1. And then we define the, we have the adjoint, as Debraj explained to us early on in the week. So this will be the Hilbert space adjoint. And it agrees with the formal adjoint on compactly supported smooth forms. So for such forms, we saw yesterday, in terms of this T and S, that T star sigma squared plus S sigma squared is equal to the inner product of the curvature acting on sigma with sigma. This was the Bochner-Kodaira BK identity. Oh, and there's of course an extra term. Maybe I don't care about the extra term. So this is actually the basic estimate. This is what I'm really interested in for Hormander's theorem. But if we want to apply any kind of functional analysis argument, this is insufficient because this inequality only holds on some subset of the space you're interested in. And so we want to try to extend this to the whole Hilbert space. You'll see later why I mean, actually for solving the Laplace equation, that's not an issue so much. You can do what I did yesterday in the compact case. You can do at the very end of the lecture. You can do the same thing here. But then when you want to pass to the d-bar equation, that becomes more complicated. So we're going to take a different approach. So to get this estimate on the whole domain of T star intersection with the domain of S, yes? Question? Okay? So it suffices to show that smooth, compactly supported forms are dense. So in this domain. And so it's been already explained, but I'll just be a bit pedantic to explain what do I mean dense. I need to have a measure of well, some way of saying that, some topology, right? So I need, in this case, I need a norm, and so of course the goal is to get this identity to hold by taking limits along smooth, compactly supported forms. And so you certainly, if you do that just in L2, this term will be okay, potentially. I mean, you have to be a little careful, because when you multiply by this curvature, you might exit L2. But the assumption that we usually take in Hormander's theorem, that this quantity is bigger than or equal to a constant, tells you that for L2 approximation, you're fine, but these things involve derivatives of the form. So L2 approximation will be problematic, and so that's why Debraj introduced the graph norm. So that's the thing that sends sigma to the L2 norm of sigma plus the L2 norm of T star sigma plus the L2 norm of S sigma. You know, some equivalent norm to this is the graph norm. I'm not making anyone crazy, but okay. Maybe it's too late to ask now. So well, I don't think, oh, you mean in the first lecture? That's because there is no S, because you're in dimension 1, S is 0, because if you have a 0, 1 form, you take d bar, you get a 0, 2 form, but you're in 1 dimension. So yeah, this is called the graph norm. It's the graph norm for the Laplacian, if you want, not for d bar.
So it depends on what operator you are trying to, what domain you are trying to approximate. So we have actually in the past approximated domain of d bar and domain of d bar star. So for that there is a separate graph norm. Here you are going to simultaneously approximate the domains of d bar star and S. So it can be thought of d bar direct from d bar star if you want, or of the Laplacian.
But why would you approximate just one?
For example, in the first one, we made a statement like compactly supported ones are dense in the domain of d bar star.
You mean, yeah, in one variable, I'm saying there is no S. This is still the one variable one, just S is the 0 operator.
If it is n variables, if you just put that domain of d bar star, so then the compactly supported ones are dense. So in the d bar star graph now.
Yes. So, but you never use that.
You never use that.
Oh, okay, so I thought you were telling him that we used that. No. We never use that. We only ever use this one. Yeah. And then this is also the one-dimensional one, but S is 0 in the dimension 1. So, I mean, maybe, I don't know if I made it clear, but the point of such an inequality is to get a lower bound on the Laplacian as a self-adjoint linear operator. You want to try to invert it. So this is the action of the Laplacian on sigma, inner product with sigma. And if you know that this is positive, then you get a lower bound on the eigenvalues. But the problem is that this is only in a dense subspace. So you want to have it everywhere. That's morally what you're doing. I'll use a different technique to solve the equation, but right. So we need this approximation. And so Debraj will do a similar thing in the afternoon for a more complicated problem, which will be used by Emil Straube at the end, in the last week, I think. But here the problem is simpler because I'm thinking about the boundary, and so that's why I want this completeness. I want to say that the boundary is infinitely far away, so I can make a cutoff function by, because it takes so long to get out to infinity. And I'm also not going to give you all the details of approximation. I could, but I don't really see the point. You can easily follow them, but I'll give the principal computations that show you why you can do it. So the theorem is just what I said here. It's smooth. So if xg is complete Kahler, actually we don't need Kahler here, then the smooth forms with compact support are graph norm dense. Okay, so what's the idea of the proof? Whenever you have differential forms that are only measurable or integrable, the usual technique to regularize them is to take a convolution with some mollifier. It's called mollifying. You take a convolution with some compactly supported thing, rescaled to make it a very steep window. You average over that and you smooth out the function or the form. So here it's a bit more complicated. You have vector bundles, and they don't have a nice global structure where you could convolve them, because you don't have a natural additive structure globally. But vector bundles are locally trivial, so they're locally like R tuples of functions. And so first you want to localize them. So you would like to say take a partition of unity and multiply all your differential forms by the smooth elements of the partition of unity, and try to regularize those individual elements. So one thing you have to know is that if you take something in the domain of S or in the domain of T star and you multiply it by a smooth function, then it remains in the domain. So once you know that, then the convolution idea will work because you're now working locally. So you're really just looking at functions in the usual way. Okay? So the key point is to cut off. Oh, well, there's one other thing. Where does the completeness get used? The completeness gets used because if you have too many of these things, you get into big trouble. So you want to first start off with a cutoff function, which essentially makes everything live inside some compact set. So you use these cutoffs to sort of do the initial localization and then partitions of unity. But in either case, you need to be able to multiply by cutoff functions. While staying in the domain. Okay, so let's have a look at one such sigma. Okay, let's say sigma is in the domain of S intersection domain of T star, and let's take chi to be some smooth function with compact support. Maybe I should have said the completeness allows you to design things like this with control over the derivatives. And you'll see the derivatives appearing in just a second. So now you look at chi times sigma, and you want to compute so the action of d bar on such a thing as a distribution. Right? And you want to show that this is still going to be in L2. If that's the case for sigma, right? The condition of being in the domain of S is that the distribution d bar of sigma is in L2. represented by something in L2. So now I just have to show that that still remains true. So, well, the Leibniz rule here says that this is chi times d bar of sigma. That's in L2, and you multiply it by a cutoff function. That's, of course, going to be in L2. And then you have plus d bar chi wedge sigma. And so now you're going to have to take the norm of this and integrate. So this guy is okay. For this guy, you're going to have the norm of the d bar derivative of chi. And if that's bounded in sup norm with respect to the metric, then you're in good shape. But that's exactly what we need from our completeness, is that we can construct cutoff functions whose gradient is bounded. So, and that's the basic idea. You then just use Cauchy-Schwarz here. So, okay, on the other hand, for the operator t, so for d bar star, you want to look at chi phi, and you want to apply t to some test form C. And remember that this guy, this chi phi, is in the domain of t star precisely if this quantity here is bounded by the norm of psi times a constant. Then this is a bounded linear functional, and you can use Riesz representation theorem to define t star. This Debraj explained this before. Okay, so now you have to imagine the L2 inner product a little bit. I'm going to be quick here. So this is multiplication by chi inner product with this thing. This is some real cutoff function for simplicity, although it could be complex if you wanted. But let's stick it to it being real. I could move it to the other side of the inner product. Okay, so now you want to do integration by parts here, well, or the product rule. This is secretly integration by parts. And so this is going to be t of chi psi phi. I should be putting sigma here, sorry. And then you have minus d, well, d bar chi wedge psi. Okay, so remember this sigma, the hypothesis was that it's in the domain of t star, so that means that it's controlled by, so this, maybe this is less than or equal to the sum of these things. So the hypothesis of sigma being in the domain of d bar star exactly means that this quantity is bounded by the norm of some constant times the norm of chi psi. But this chi is just some cutoff function. So it's compactly supported function, so you can just bound it by its supremum, so you can get rid of this term here. So that's the first term there. Second term here, it's a similar story. This is C2 norm of d bar chi wedge psi. But again, the gradient of d bar is bounded in the norm defined by the metric uniformly. So again, you can absorb that into this constant. So that shows you that cutting off does not alter membership in the domain. And so once you know that, then you just can localize your whole problem, use convolutions to regularize the operators. And that's, I think, all I want to say at this stage. The rest of the details would be pointless to present on the board. So. Okay, so now we're ready to state Hormander's theorem. So let me just, okay, so let's let X and G, so X is going to be a complete Kahler manifold, but G is just going to be a not necessarily complete Kahler metric. Okay, so there exists a complete Kahler metric, but it might not be this G. And then we have the E, a holomorphic line bundle, and then we have a smooth Hermitian metric H for E. So now let's assume theta G H is greater than or equal to some constant times the identity of lambda and Q. Answer E. For some C bigger than 0. So this is now a constant. Okay, then the conclusion we all know by now. So then for all E valued NQ forms, phi such that d bar phi equals 0, and the integral over x of phi squared with respect to these metrics and the volume form of G is finite. There exists U E valued N Q minus 1 form such that d bar U is phi and the integral over x of the same thing, but for U is less than or equal to 1 over C times the norm of phi squared. Okay, so this is a statement we've seen several times now. So I want to prove this. Okay, so let's first case, we're going to assume that G is complete. It's a complete metric. So we know such a thing exists, right? So it's not the G we're going to ultimately use, but for now, we're going to assume we have a complete one. So, and then, so then all this approximation business tells us that this basic estimate actually holds on the whole Hilbert space, well, on the whole domain of T star intersection domain of S. So by approximation, we have that T star sigma squared plus S sigma squared is greater than or equal to C norm sigma squared for all sigma in the domain of T star intersection the domain of S. Okay, so I'm just going to repeat the argument of the functional analysis lemma in this case, just quickly. It's just an opportunity to remind you. Except remember that the functional analysis lemma wasn't for such things. So it was there was no term like this in the functional analysis lemma. This is a thing you were asking about before. Okay. So we want this term to go away. So in fact, we can do that by we're going to take our Hilbert space H2 to be the kernel of S. And this is not the only way to do this argument, but this is the one that I chose to do today. So, the kernel of D bar is a closed subspace of this Hilbert space L2 NQ. And so you're certainly allowed to take any closed subspace of a Hilbert space, and you still have that. And then on this subspace, you have this estimate with this term gone. So here, norm T star sigma squared is greater than or equal to C norm sigma squared. So I want to emphasize that the order in which you do these things is important. So first you have to establish this identity on the whole Hilbert space, and then you can restrict to the closed subspace. You won't know that you have this estimate if you just restrict to the closed subspace initially. So, because it's not closed, I mean, it's closed only in the relative topology in that case. So, and that's not good enough. Okay. And now we have our operator T. So this is going to map H1. So this H1 is just L2P Q - 1. N, thank you. And usually it maps to L2NQ, but because d bar squared equals 0, this is automatically in the kernel. So it does actually map into H2. So the compatibility condition is part of what allows you to restrict to the kernel. Okay? Okay, so now I'm in the situation of the functional analysis lemma, and I could just use it, but let me just remind you of the argument quickly. So let's let lambda, say from H1 into C, be defined by, so you take lambda on the image of T star, you define this to be, so sigma phi. Phi is the form in the theorem. We fix one of these. Okay? And then you define lambda of V equal to 0 for V orthogonal to the image of T star. Okay. So, so this linear functional on the image has some norm, and when you extend by 0, you don't change that norm. Okay? So we just, to check the norm of this linear functional and see that it's finite, it suffices to just look at this identity. And so then we look at so lambda phi, or sorry, lambda of phi of sigma, of T star sigma. So that's equal to sigma and phi, and that's less by Cauchy-Schwarz, that's less than or equal to norm phi, let me put squares here, times norm sigma squared, and then the norm sigma squared is less than or equal to norm phi squared over C times T star sigma squared. So that shows you that it's bounded, this lambda is bounded, and this is an estimate for its norm. Okay? And then by the Riesz representation theorem, you produce, no, I'm defining it that way. That's the definition of lambda. So I define it to be, so my Hilbert space, H1, it has the image of T star in it. That's some subspace. And then I define this functional on that subspace. And then on the orthogonal complement, I define it to be 0. And then I extend this functional by continuity, if it's continuous, to the closure of the image. So whenever you have a closed subspace, the orthogonal complement plus that closed subspace is the whole space. So this is just the definition of lambda. Is that okay? Okay. In fact, another way to say it is that if you define lambda on this subspace and then you take an extension of the smallest norm extension you can, and this is it. There's only one. So, okay, so by the Riesz representation theorem, there exists some u in H1 such that So U acting on sigma is just lambda of sigma complex conjugate. So far we have a U, and Riesz representation theorem also tells you that this element has the same norm as lambda. So in particular, it's less than the norm of phi squared over C. And so the only thing left is to prove that it satisfies the d-bar equation. And for that, we restrict to the image of T star. So if we look at U of T star of psi, let's say, so that's going to be lambda of T star of psi conjugate. And lambda of T star of anything is inner product of sigma with this anything. And complex conjugate says that this will be so phi. I said that a little off, but you know what I mean. And this is exactly the d-bar equation. This is what we mean by the d-bar equation. It's in the sense of distributions. So if you just use psi to be compactly supported, for instance. So. Okay, so that proves Hormander's theorem when you have a complete metric. That's not a very difficult theorem, so it makes you a little nervous how easy it is. If you set up all the geometry correctly, and I don't just mean the things that I explained, but also the things that Debraj explains. This is also geometry for this problem. Then it comes out very clean. Okay, so now what about the general case? So this possibly non-complete metrics. Okay, so before I do that, let me do a little bit on comparison of metrics. Okay, so suppose that we have two metrics. So let's let, say, G and gamma be two Hermitian metrics. Such that, say, gamma is greater than or equal to G. What that means is if you compute the norm of any vector with respect to gamma and with respect to G, the gamma norm will be bigger than the norm than the G norm. Okay. Okay. So now what I want to do is to understand these pointwise norms of these differential forms in a convenient way, so that I could compare the pointwise norms. So I know how vectors compare. The dual thing should compare the other way around. But actually, it's not just the norms I'm interested in. Let's see what I mean. So, okay, so to do that, it's convenient to choose an orthonormal bases for these metrics. The thing is, if you have two positive definite things, then they're both diagonalizable, except that these are not matrices, they're not linear operators. These are quadratic forms, or bilinear forms. So actually, you cannot talk about diagonalizing bilinear form. But you can talk about diagonalizing one with respect to another. So I'm just going to assume that you know that. So we're going to choose a frame for, say, T10 x. This is all local. Okay? You can even do it at a single point for what I'm doing here. So let's call it, say, theta 1 up to theta n, so such that the metric gamma is diagonal with respect to the metric g. So what that means is that this metric g is going to be, so theta 1 times theta 1 bar plus theta n times theta n bar. And then gamma will be, say, lambda 1 theta 1 times theta 1 bar plus lambda n theta n times theta n bar. So this you can always do for any two metrics. And the hypothesis of the domination of G by gamma means that all these lambdas are greater than or equal to 1. Okay, so now if you take any, say, eta in... yes, thank you. Is it? Yeah. So actually, I don't need a section. I can just do this point-wise. Let's say I have a vector over some point in here. Then I can always write this thing as some numbers. So its eta will be, say, eta alpha j bar. And now we were using a very particular frame in the past, the dz's and the dz bars. But now we're going to use these thetas. So these coefficients are different functions than the other ones. But anyway, they're just a different frame. Okay, so here we have, say, theta 1, wedge theta n, wedge theta bar j. So this just means theta 1 bar to the j1, etc. Just the same as before. And then we have some frame E alpha that I don't care that much about. And so what's the norm of eta with respect to, say, G and H, norm squared? Well, it's actually, so these are just orthonormal things, so they don't have any norm. So it's just, you just take the norm of this vector in E. So it's just the norm of eta alpha j bar E alpha squared, and you have summation over all the possible j's. And this is just measured with respect to the metric h. This is a point-wise thing, so I'm not saying this is global. On the other hand, what is the norm of eta squared with respect to gamma? Well, so this metric here, sorry, this one here, says that if you have the vector, so if you look at the dual basis, say v1 up to vn, then the length of v1 is lambda 1, right? And the length of vi is lambda I. But it means that the length of theta I is 1 over lambda I. That's because the dual is the inverse. Okay? So this length here is going to be the same numerator, so sum mod j equals q. So eta alpha j bar E alpha squared h. But then you have divided by, and you have this lambda 1, right, lambda 1 up to lambda n times, and then I'll write it as lambda to the j. So that means lambda sub j1, maybe I should better write it that way. So lambda j1, lambda jq. So you see that this norm is actually less than a norm with respect to g. So the norm, it reverses the direction. It's not surprising, but actually the problem is that this is not the right norm because, did I ever write the, yeah. So it's not just, that's not the only place where the metric appears. You also have this g. And what happens to dv gamma? Right? So dv g is just, so square root of minus 1 to the n, theta 1 wedge theta 1 bar wedge theta n wedge theta n bar. It's just the analog of the Lebesgue measure. But if you compute dv sub gamma, that's a lot like this, except you get a lambda 1 for every one of these things. So it'll actually be lambda 1 product, lambda 1 up to lambda n times dv sub g. So and when you multiply, you see, when you multiply this by dv, that's the measure you want to compare, right? So then you see that still, so this, a priori, this could cause you problems in the inequality. But when you use n-q forms, it doesn't, because the n gives you this denominator. Okay, so that means that eta squared gamma h dv sub gamma is less than or equal to eta squared gh dv sub g. And now what's the point? So it's an easy exercise to show that if you have if, say, G is a metric and, say, G tilde is a complete metric, then for any positive number epsilon, G plus epsilon G tilde is complete. So it's just, if you want the geodesics to live forever, you have to have just some of the measurement coming from a complete metric. It's an easy exercise. Okay. Maybe if you want to be convinced by this, so another way of seeing completeness is you look at balls. You look at a ball less than a given radius, that should be compact. But the ball, if you have a bigger metric, then a ball of the same radius is actually smaller. So by taking a bigger metric, you're looking at subsets of already compact things. So the point is this is greater than or equal to epsilon times G tilde. That makes the ball compact. Okay, but it's also greater than or equal to G. So the completeness you prove by showing this, by observing that this is greater than or equal to epsilon G tilde, but the estimate we actually need is this one. And from that, you get this inequality. Okay, so now you go back to your Hormander's theorem, and you take this G epsilon metric, tells you that you can solve the d-bar equation with some dependence on epsilon in the metrics. But the upper bound doesn't have, so let me say this carefully. So this process that you go through, the U that you produce, it depends on all the data. So in particular, if your metric depends on epsilon, then your solution U also depends on epsilon. So that's problematic. On the other hand, the data phi does not depend on epsilon, it's fixed. These metrics can still depend on epsilon, but if you take a limit as epsilon goes to 0, which you can do by basic Lebesgue limit theorems, like a monotone convergence in this case, right? It converges to this thing. So in particular, this quantity is bounded independent of epsilon, even though the U depends on epsilon. But the norms are controlled by the monotonicity over there. And so what it means is that your U epsilon actually lives in a single ball in a single Hilbert space, not in a family of Hilbert spaces anymore. Okay? So there's a famous theorem in the Hilbert space case called Alaoglu's theorem, and then it's generalized to many, many Banach spaces, in fact. But the point is that if you have something in the unit ball, then it's weak star compact. So you have a weakly convergent subsequence. But our d-bar equation is already a weak equation. So all you need is a weak convergence. So you extract this convergent subsequence, and you get your same estimate in the limit. So that, I think that answers your question. It's a clever trick, I think. So. Yeah, it applies to everything. Yeah. It's and this is much simpler than what you are opting not to completely do wisely. I think this is. It depends what you want to do, but if you're interested in regularity up to the boundary, this is useless. But if you just want Hormander's theorem, it's actually an incredibly simple theorem. So that's part of its power as a tool. It's not actually difficult. Okay, let me, Debraj was asking just now whether or not this kind of thing applies to, for example, pseudo-convex domains. And it does. I'm going to show you that it applies. Actually, to even much weaker class of manifolds called weakly pseudo-convex manifolds. Definition. A manifold X is weakly pseudo-convex. Let me write it. Pseudo. We never write this, so we never know how to spell it. if there exists a smooth plurisubharmonic exhaustion. See, psi from X to R. So this is, the strongly pseudoconvex is that this is a strictly plurisubharmonic exhaustion. I'm saying you don't need strict plurisubharmonicity. So for example, compact manifolds satisfy this, but they're never strictly plurisubharmonic. But there are many actually interesting manifolds. For example, if you take a complex manifold and you blow up a point, which is an example I didn't give, but it's in the notes, then that is no longer strongly pseudoconvex, even if the initial manifold is strongly pseudoconvex, but it is weakly pseudoconvex. So you can apply this theorem in that situation as well. Okay, so here's the point. So proposition. So every weakly pseudoconvex, say Hermitian, so Kahler manifold is complete Hermitian, respectively Kahler. Okay, so I'm going to quickly prove that for you. It's a very simple proposition. And so this gives a lot of interesting examples of manifolds to which you can apply this theorem from complex analysis. Okay, so for example, pseudoconvex domains. What's the proof? So remember, I said at the beginning of the week that if you have a Hermitian, or maybe it was the second lecture, a Hermitian metric determines a metric form. It's a two-form, which, well, it's a 1-1 form. And Kahler exactly means that this form is closed. Okay, but so let's pick a, say, Kahler, or pick a Hermitian metric, say G for X, which is Kahler if X is Kahler. Okay? So, and now we're going to define omega G. Well, omega G is the going to be the form for G, and then maybe I should have said the correspondence between forms and metrics is 1-to-1. So remember, the way you get the form is you take G of Jx comma Y, and conversely, the way you get the metric is you take omega of X comma Jy. Okay? So, or Jxy, whichever one. So I just have to give you the Kahler form, or the Hermitian form. So it's going to be the form for G plus square root of -1 dd bar e to the 2 psi, where psi is this exhaustion that we have. So notice that if this form is Kahler, so this is a closed form, this is always a closed form, so this one will be. So this is Kahler if and only if this is Kahler. Okay, so I claim that this metric is complete. So let's check. Let's compute this. So dd bar e to the 2 psi is d of e to the 2 psi times 2 d bar psi, which is 2 dd bar, 2 e to the 2 psi dd bar psi plus 4 e to the 2 psi d psi wedge d bar psi, which is 4 d of e to the psi wedge d bar of e to the psi. Okay? So now if psi is an exhaustion, an exponential is an increasing function, so e to the psi is also an exhaustion, right? And what does this inequality say? Oh, sorry, I'm missing this term. I'm going to give it up by just taking inequality, and this is where I'm using a weak plurisubharmonicity, okay? So what this says is that this is actually greater than or equal to This omega g, well, it's a metric, so it's a non-negative form. I'm just going to forget that one as well. And I'll have here 4d e to the psi wedge d bar of e to the psi. But actually, this inequality here is the same thing as saying that d e to the psi squared with respect to omega is less than or equal to a quarter. So that can be one of the exercises today to show that this exactly means that. And this is a real valued function, so this d, this is just, say, a half of a straight d. Okay. So you can bound either one, or the bound is 1 in this case for this metric, for d of e to the psi. So my equivalent condition for completeness. So that shows you that you have a complete metric, okay? So I think this could be a good moment to stop.